Good morning. I want to give you guys an example of how to do one of these gravitation problems that you're going to need to do today. Let's get started. A satellite with a mass of 1,000 kilograms is orbiting planet X with a mass of 10 times 10 to the 24th kilograms from 700 kilometers away. How fast is the satellite moving? What is the acceleration of the satellite? And what is the gravitational force between the satellite and the planet? Start with A. It might actually be easier to do these in a different order, but I'm just going to dive into the problem. I know that the gravitational force for the satellite is going to be equal to my centripetal force. It has to be equal, otherwise we don't have an orbit, it's going to be crashing. Okay, so I know that Fg is equal to gm over r squared, and that m is the satellite and the planet. And then my centripetal force is based off of the mass of the satellite times the acceleration and its centripetal acceleration. Let's do some simplification here. I can cancel my mass of the satellite on both sides, so it didn't even matter that I knew the mass of the satellite right now. We didn't need it for this part of the problem. Let me rewrite this. G, mass of the planet, over r squared, and r is going to be that 700 kilometers is equal to AC. Now, the formula for centripetal acceleration is v squared over r. We're looking for v in part A. Let's simplify this, cancel out that r, cancel out that squared, so I'm going to be left with g, the mass of the planet, over r is equal to v squared, so I'm just going to square root that, so it's just v. And then let's plug in some values. The value for g is 6.67 times 10 to the negative 11th. The mass of the planet is 10 times 10 to the 24th kilograms. And we're going to divide that by r, which is 700 kilometers. I'm going to convert that to meters. So it's going to be 700 times 10 to the third power of meters. Let's plug that into the calculator. You might be wondering, oh my God, how do I plug this into a calculator? The thing that you're going to want to do if you have a TI-84 is to do second and then do the comma button. That's going to say EE. So you're going to see something like I'll type in square root 6.67, and then I'll do second comma, and it's going to say E. And that means times 10 to the. So I can write 6.67 and then the E and then negative 11, and that means the same thing. Okay, that's just for your calculator, not for writing down your answer. All right, G times the 24th power divided by 700 times 10 to the third power. That's going to give me a really, really fast velocity of 30,868 meters per second. That is fast, 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 but of course these are fake numbers. All right, so that's part A. Circle that. Oh, that's a terrible circle. Let me try that again. There we go. Then let's do part B. Maybe I'll switch colors. Let's do this color. So that was A. This is B. What's the acceleration of the satellite? Oh, well, now I know my velocity, so I can just say AC is V squared over R. So I could plug in my V squared, which is going to be that 30,868 squared, divided by my distance in meters again, 700 times 10 to the third power in meters. Let's plug that in. So I want my number from before, squared divided by 700 times 10 to the third power, and that's going to be 1361 meters per second per second. Again, that is a big number, but these numbers are fake. The last part is to find the FG between the satellite and the planet. So I know acceleration. Remember, FG is equal to FC. I can calculate this two different ways. I'm going to go the easy route. Since I know that my gravitational force between my satellite and the planet is equal to the centripetal force, I can just say, oh, well, this is going to be equal to A, the centripetal, or uh, is equal to mass of the satellite times that centripetal acceleration. So the same thing that we said over here. This is just Newton's second law, mass times acceleration is equal to your force. This is why we had to have the mass from the satellite for this problem. So 1,000 kilograms times that centripetal acceleration, which we got before, which is 1361 meters per second per second. So I do that in the calculator. I'm going to get a big number, so I'm going to put it in scientific notation, and that's going to be 1.36 times 10 to the sixth power of newtons. That's a big force. Oh my gosh, my circles are just struggling today. All right, so that's just an example of how to figure this out. I want to do one other problem with you guys. Let's play with planet X again. So I know the mass of planet X is that 10 times 10 to the 24th kilograms. Let's say the radius of that planet is going to be, 10 times 10 to the sixth power of meters. And I want to know what little g is. Now remember, big G is your gravitational constant. Okay. That's that 6.67 times 10 to the negative 11th and some unit that I never remember. Little g is your acceleration due to gravity. So on Earth, that's 9.8 meters per second per second. Okay, this is how much acceleration is happening to make objects fall towards the center of that planet. Okay, so we're on Earth. When we drop things, everything falls towards the center of the Earth, and at this rate. What if I want to find little g for this planet? Well, I can use that Fg equals g mm over r squared. And remember that Fg is equal to mass times acceleration. And the acceleration in this case is g. So the mass of whatever object you have, so me standing on the planet, you standing on the planet, a book resting on a table, times g, that's normally our Fg, right? So if I have a book sitting on a table and I want to know the gravitational force, I would say Fg equals mg. Well, the mass would be this, and the g is the acceleration due to gravity. So if I take away one of these masses, that means this becomes little g. So if I take away the mass, this is going to become g. G equals g. So that means if I'm looking for g, I just need to have big G times the mass of the planet divided by the radius of the planet squared. So if I was going to do that for planet X, I would say 6.67 times 10 to the negative 11th times the mass of my planet, which is 10 times 10 to the 24th power, and divide that by my radius squared, which is that 10 times 10 to the sixth power of meters, and don't forget to square. If you forget to square, your number's going to be wrong. So let's plug it into the calculator, 6.67 times 10 to the negative 11th times 10 to the 24th power divided by 10 times 10 to the sixth power squared. And that's going to give me 6.67, which makes sense because these numbers are all tens. 6.67, what would our unit be? What would our unit be on Earth? Meters per second per second. I think that goes through all the different types of problems that you need for today. If you have questions, please ask me in class or email me. I'm here to help. Bye.